Summarizing what we discussed on Tuesday. So the two main points I tried to make was that, first of all, if you phrase the information paradox from the point of view of an asymptotic observer, then there's a natural, in principle, resolution of the paradox, which is the idea that exponentially small corrections can unitarize the radiation, and this is consistent with generic expectations from quantum statistical mechanics. On the second part of the lecture, we discussed another aspect of the problem, which is reconciling this idea with the smoothness of the horizon. And there we found that the Hawking particles, when they're produced, they are produced in entangled pairs. And we found this conflict because these particles which are produced have to be entangled with each other, but at the same time, the outgoing particle has to be entangled with the earlier radiation, and this leads to a violation of monogamy of entanglement. And also, we argued that the entanglement between the two particles has to be very specific, and this is sort of seems to contradict generic expectation from statistical mechanics, which is that if you take a big system and you divide two parts, the entanglement between the two subsystems will not be specific, but will be generic. Let's say the details of the entanglement. Now, a lot of these discussions were not very precise. So there were very many important questions about how exactly we define entanglement entropy in gravity, how do we define a subregion, and okay, one could think that perhaps there's a loophole there that we have missed, and okay, so it's not very precise. So today I will try to phrase an equivalent paradox in the context of AdS CFT, where we will see that some of these problems become more precise as statements about the operators in the dual conformal field theory. Okay, so in AdS CFT, again, if we phrase the paradox, information paradox, as a question about whether evaporation is unitary, then if we accept the AdS CFT correspondence, the answer is obvious that evaporation is going to be unitary, because in the CFT dual, the process can be described unitarily. So we can form a black hole, let it evaporate in AdS, and in principle we can we expect this process is going to be unitary. But as we discussed, the question we want to address now is what happens at the horizon. So now, in flat space, we have been talking about evaporating black holes. But in AdS CFT, it is easier to work with large black holes because we understand them better from the CFT point of view. And at first, you may think that since large black holes are in equilibrium and they don't evaporate, then there will be no paradox to consider. But as we will explain in the next few slides, you can actually find a similar paradox for big black holes in AdS, even though they're in thermal equilibrium. So the question we want to address is whether the horizon of a large AdS black hole is smooth.
That means about Hawking page transition?
Yes. A large black hole poses specific heat. It's a big black hole in AdS.
But in particular about Hawking page transition? No. You want to
yes, I want to work in a regime where this is the dominant configuration. So the question we want to ask is what happens at the horizon of this big black hole, and in particular, this means that we have to understand how to represent local bulk physics in AdS from the point of view of the CFT. And let me review for you a little bit one way of doing that. So we will be working with a CFT at large n and large coupling. And we will use what is called the Hamilton-Kabat-Lipschitz law construction of local bulk operators, which is roughly the following. We have we consider some field phi in AdS, a scalar field phi, which is dual to an operator O in the CFT. And we know that this field phi obeys the Klein-Gordon equation at large n. And it also has some sort of boundary conditions that if you take the field and you take the limit where the point goes near the boundary, then this field should be identified with a dual operator, at least for the purpose of computing low point functions on a state. So you can think of this as some kind of boundary value problem. So you have AdS, you have a field in the interior of AdS, and you have some boundary conditions on the boundary of AdS. And in principle, you can invert this problem, and you can express a bulk field in terms of the boundary operator by solving some Green's functions in AdS. And in this way, you can write down a formula for a CFT operator. So here I have emphasized that this object is an operator in the conformal field theory, which seems to depend on the coordinates of AdS. And it can be expressed in terms of one way of doing that is to Fourier transform both sides, like let's say in frequency and in angular momenta, And then you can invert this mapping more easily. And then you can express this object in terms of the Fourier modes of the single trace operator of the boundary, multiplied by some wave functions, which are solutions of the Klein-Gordon equation on the AdS background. And you have to integrate overall frequencies and some overall possible angular momenta. And then what you can check is that at large n, the correlation functions of this object are the same as those that you would calculate naively for a free scalar field in AdS. So in particular, if you take 2 points in AdS and you compute the commutator between this operator at 2 different points, you find that it's equal to 0 if the points are space-like with respect to the AdS metric. So now this construction is not entirely satisfactory. There are some issues, several issues. One is that sorry? Capital omega, the angular variables in AdS. So I'm working in global AdS, and these are the angular variables. And f are solutions of the Klein-Gordon equation, which have to be normalizable at infinity. So there are some issues with this construction. First of all, to write down this equation, we have to assume that we have an AdS background. So we cannot prove it. We have to assume the classical background. And we're computing the quantum fields on top of that background. So we're sort of using our knowledge. We assume that the dual geometry is AdS, and that's why we're using the solutions of AdS. And so this is not a derivation. It's some kind of construction assuming that we have an AdS dual. Another issue is that this construction is perturbative in 1 over n. So the statement that this field is local with respect to AdS metric is true only at large n. If you include 1 over n corrections, and if you compute this commutator inside a correlator, then 3-point functions start to become important, and you find that this is not equal to 0 anymore. It's equal to 1 over n times some corrections. And then one way of fixing that problem is by correcting this map perturbatively in 1 over n. So you add some double trace operators here with a 1 over n coefficient, which are selected in a very special way in order to cancel the non-locality that you get at subleading order, and so on and so forth. So this is not entirely satisfactory, but at the moment, I don't know of any other way of representing local physics in AdS.
The last thing you said, does that just amount to solving for the bulk field, including interaction?
Exactly. That's right. Exactly. So presumably, you can do it to all orders in 1 over n. Well, if you at least not. Yes. Now.
Sorry, can I ask
yeah.
a question, which is an aside, so
yeah.
But just to ask, suppose there was a large n theory, like a vector model,
yes.
which didn't have anything like a
yes.
bulk.
Yes.
I could, of course,
yes.
at the leading order such a thing.
Right.
But presumably, once I start including
exactly.
it won't be any local bulk.
Yeah.
Right?
So that's right. I don't know if anybody has showed it in some detail that you must have a gap in the spectrum in order to be able to reproduce. You should not have high spin fields. In order to reproduce local bulk physics. But I think that's the expectation.
And just sorry,
yeah.
one more
Yeah.
thing. This is just at the level of differential equations is a strange problem to solve.
Yes. So it's a sort of ill-posed boundary value problem. At least maybe not in AdS, but if we go to the
say it's not a hyperbolically whatever.
yeah.
Oh, you mean because you're giving the data in
Global
time.
height.
That's what you mean.
Yeah. Actually,
Space.
yeah. And actually, we will come to yeah. Go ahead.
Sorry, and the data has to obey equations of motion. In the sense that the thing on time is not an arbitrary function.
Right.
Right. For instance,
What is that equation?
let's take a minimally coupled scale at the bulk. Minimally coupled massless scale at the bulk. Then in AdS 5, its frequencies are 4, 5, 6, 7, 8, 9, 10. So if you know what the field is doing in a patch of length 1, you know what it's doing everywhere. So you don't need to know it everywhere. Knowing it on some part of the boundary is enough to know it everywhere, and therefore to reproduce the whole solution. So
Right.
it's
Right.
very strange kind of.
Yeah. So it's not very satisfactory. Also, this mapping is sort of non-local in time. So as you can see, these objects are
Sorry, just to answer, you're saying that I thought that in the boundary theory, if you know the dimensions of the operators, you would know what values omega would take.
What values omega would take.
And
So
then
this will be true if you do it around AdS, right? If you do it around a black hole, as we will do in the next slide, then this omega can really be continuous. But if you expand around AdS, you will have support only on the discrete frequencies.
Right. Okay, you should come back to what did you mean by saying you need? I didn't understand.
So you might have thought that roughly from the theory of differential equations, you might have thought you need to surround a problem by boundary conditions. So you might have thought you need to know what phi is doing on the whole boundary.
For all time,
For all
not just
time.
in the band.
Yeah, I'm saying just in the band is enough. And then there is all these stories about how much, if you want to know phi for some region inside here.
How
Yeah.
much of the band you need.
Yeah. So it's a,
Yeah, so there are issues
just
of,
this differential equation is an interesting problem.
yeah. So,
Structure to just this differential.
yeah, so there's this ambiguity in where you place the band if you do it around ADS. There's yet another ambiguity, which is that you can, this is not unique, even around ADS, you can sort of localize the support of this function on subregions. For example, if we look from above, if you take a point, you can reconstruct this point using this prescription by using the entire boundary, or you could select some ADS linear wedge and try to reproduce it here. And then as there's also some ambiguities, you can select many different overlapping wedges, and some properties of like quantum error correction appears. And so there are many issues here. Also, this field is a field in gravity, so you could ask how is it local? I mean, how can it be local? Or so this is a field which is in some particular gauge. We have selected the coordinate system, so this is supposed to be represented in a particular gauge choice. Okay, so there are all these issues, but I don't think there's any.
It may not be issues, they may be.
Yeah. Okay. So now, if we have this formula, we can also just let me make a small comment. We can also, this is the Fourier mode, so you can write it as an integral over the boundary with some. Yeah.
Just to say again, I mean, of course, this point has been made ad nauseum the last 5 years. But anyway, just to say again, it means that there are many inequivalent boundary representations of the same bulk operator.
Yes. That's the
Yeah, exactly.
that's the connection to quantum error correction.
Yeah.
So you can also
You have to check that all that is consistent.
right. So here also these guys are Fourier modes, so we can rewrite them in position space as integrals over the position space, and we can change the order of integrations, and then you can represent the same thing in a different way. So you can represent the bulk field as an integral over position space on the boundary, and here you have a kernel that you get by changing the order of integrals.
I'm sorry,
Yeah.
this is probably taking you far away from what you want.
Yeah.
Just to understand. Suppose now we went to the quantum effective action,
Yes.
and there were higher and higher orders and derivatives. Now it's not clear that just the boundary value will be enough to determine the bulk, right?
You mean the boundary value of this guy, or the entire tower of single trace operators and the derivatives?
Yeah, good. I was thinking of just trying to work for effective integrating out loops. I keep everything.
So we keep all operators on the boundary.
I keep all operators,
Yeah.
but I integrate out the loops. I get a quantum effective action.
Right.
I was thinking in the bulk.
Mm-hmm.
A quantum effective action in the bulk,
Mm-hmm.
which now is not a two derivative.
Yeah.
So it's now not clear to me that giving boundary values will determine the bulk, because it's not two derivative anymore. Is that the bad way to think?
I don't know. I would have to think about it. I don't know. I don't know if anybody has looked at loops.
Well, you wouldn't expect that if you gave it in the full band in global, you would be able to reconstruct.
I was just thinking that even if you give it the full band, that's a property of second order differential equations, right? That surrounding the problem determines the solutions inside. If it was a fourth order differential equation, you need to surround it, plus one more surround piece of data. Right, I mean, second order differential equation means condition and first derivative, which is the same as surrounding, because that's like initial and final. But if you have a fourth order differential equation, you need four things. So that's two pieces of data and two pieces of data, so two pieces of surrounding data.
Why can't you have 4 pieces of data on the same boundary?
You can, but that's not, let's say the boundary should be thought of like initial and final space.
Yeah.
Because it's all around your space time. So initial, final is like boundary. So that's why just boundary conditions were enough for a second order.
Right.
Okay, sorry.
Okay. Right. So then we can also write in this way, where there's some kernel you can calculate, and let me emphasize this is not a bulk boundary propagator. It's some other kernel. It has to satisfy normalizable boundary conditions at infinity. And okay, anyway, so in this way we can get this object that has some properties of a local bulk field in AdS, and now we want to do the same thing in the presence of a black hole. Well, that's a good question. I mean, it's very ambiguous, right? As we discussed here, you can try to support it in smaller regions.
But that picture suggests.
Oh no, this picture, please, don't take it seriously. This picture is just to indicate that in some sense, if you bring the point very close to the boundary, you can try to support it on a very small region. But if you put it deeper, then you need a larger region on the boundary. But it's.
But there is no sense
You can. There is. I mean, in this picture, you can. So this is ambiguous, right? There are many. It's not unique. So if you take a point in the bulk, a particular point, you can consider the causal diamond that corresponds to, like, let's say, a wedge that barely contains this point. And then you have a causal diamond in the bulk, and then you can try to support the.
So it's possible to support it as smaller.
Right. There's some technicalities that if you try to do that, then this is no longer a function, it's a distribution. You cannot really write this as a function. And this will become, it will play a role in the case of the black hole as well, and maybe I will mention it a little bit later. So
you just try to use the Rindler wedge?
you cannot really write down a function in the Rindler wedge. You can write down something in Fourier space, so you can use this representation. But if you try to actually do the integral and invert this to the summation and the integration, you find a divergent integral. So the way to interpret that is that this object should be thought of as a distribution in the sense that you should use it only inside correlators, because then if you do it inside correlators, this will be multiplied by the correlation function of the boundary operators, and those are suppressed by precisely the right factor in order to cancel the divergence.
Okay, that's fine.
Yeah, that's probably fine. So now we want to do something similar in the case where we have a black hole in AdS. So now the expansion will be similar. So let's start from the bulk point of view. So we have a big black hole in AdS, and we take a scalar field in the background of the black hole, and then again we can expand it in a set of modes. Now the difference is that the frequencies are going to be continuous, and okay, we have the angular momenta also, which I will drop from now on. I will not talk about angular momenta; don't play any important role.
These modes have got boundary conditions.
Yeah. So these modes have no boundary conditions on the horizon. So they're linear combinations of ingoing and outgoing modes, but they have to be normalizable at infinity. And that's the reason we get continuous spectrum. We only impose boundary conditions at infinity. Now, these modes are multiplied by some operators in the semi-classical quantization of the field, and these operators have to obey the canonical commutation relations and some commutated with Hamiltonian. And if we assume that the black hole is in the analog of the Hartle-Hawking state, so we consider the AdS Hartle-Hawking state, then these modes are going to be thermally populated. So,
I mean, in the CFT, where is this continuum of energy coming from?
The gaps, if you have a black hole, then you're looking at a state which has very high energy. So in that regime of energies, the gap between states is like exponentially small, it's very small. And you're looking at the correlation functions on top of that state. So you get a continuous spectrum, approximately continuous spectrum.
So is there some scaling also that needs to be done to make that densely populated spectrum into continuous?
Well, in the larger limit, the gap goes to zero. So from the semi-classical analysis, you can also see the discretization of the spectrum.
The gap will always be one, right? Quantized in units of one.
No, so at very high energies. So in the free theory, the gap is 1, right? But then you have e to the n squared states at every given level. And if you turn on interactions, it's believed that they spread out. So, well, if the spectrum is chaotic enough, they will spread out all over the place, and the typical gap will be of order e to the minus n squared. So now we want to understand how to reconstruct something like this in the case from the CFT point of view. And so now this black hole in AdS will correspond to some microstate, some particular pure state of n equals 4. We think of it as being a state on the sphere. So we have a sphere, n equals 4 on the sphere at high temperatures, and we take a particular, we take a particular pure state psi, whose energy is over the n squared. So this is in the regime which is dominated by a black hole in the bulk. And then we will assume now we will discuss to what extent we can prove this, but we will assume that single trace correlators, when you compute them on that state, factorize.
Sorry,
Yeah.
But what this gap, is there precise, in the field theory, we're not dealing with around a particular state. We're dealing in an answer.
Here I'm looking at a state.
But let's say I go back to just the internal black hole.
Okay, so we're in a thermal ensemble.
We're in a thermal ensemble. And now you've made this observation that there is no gap
Yes.
in the spectrum of solutions of some differential equation.
Yes.
And I want to see if I can take that and make that precise field theory.
Yeah, so I would say you have to look at trace e to the minus beta h times the two-point function you want to consider, O at t,
Fourier transform.
O 0. Fourier transform is a complete set of states. And then if you assume that the matrix elements of this O are generic enough, that the click between all kinds of, this is related to the eigenset thermalization hypothesis, the assumption that the matrix elements of this object among different energy eigenstates are generically non-zero.
Fine. But the statement is that the Fourier transform has support at all omega.
Well, you mean the exact guy or it has support at discrete frequencies, but the gap is over the e to the minus n squared.
Right. I mean, I want to translate the statement that the differential equation had no gap into some quantity that I can measure in field theory, and that is basically, to the extent that you can do the gravity approximation, this is the statement that this Fourier transform is support over continuous.
That's right. Exactly. Now, we don't want to do it in this particular,
Since you use QGP, I guess you really meant quad pure plasma, pure state. What do you mean?
Well, I'm sorry, maybe
as an analogy.
As an analogy, I just meant a pure state of the n equals 4 Spey-Mills as an example, right, at high temperature.
It's not a bad analogy, because you might expect something similar in a confining theory, right? When you heat it up past the confining transition.
Right.
Okay.
Well, I use a word to describe the gas of the n equals 4 at high temperatures, but maybe it's not accurate. Right. But as I tried to discuss yesterday, on Tuesday, the problem is not, the main problem is to reconstruct a smooth interior for a very large majority of states, not for particular states. So we don't want to work with a thermal ensemble. We want to work with pure states. So we'll consider a pure state psi, which will assume that it has very,
Is the statement that the correlator has supported all omega, or that it has an imaginary part at all? Let's remember just how the two-point function goes in pure AD, in global ADS. There, the two-point function once again has support at all omega, but it has poles in particular. And those poles are the places where the...
Okay, so this would have poles.
This will have imaginary parts.
That's right. That's right. Oh, in the approximation where you ignore the... That's
so
right.
So the statement is that it has a cut.
That's right.
It just goes over.
Right.
Okay, thank you. Yeah,
Right.
that's right.
That's right.
Okay, so that's the translation.
Right. But now we want to deal with a slightly more difficult question, which is what is the behavior of this correlator on a pure state?
I have
Yeah.
confusion from the previous. So your H and omega, H and d omega, this commutator is minus omega d. This minus omega is as observed by asymptotic observer, or something?
Well, I mean, this Hamiltonian is the boundary Hamiltonian. It's the Hamiltonian that the asymptotic observer would define. And the minus sign is not surprising. It's just telling you that if you act with a lowering operator, you lower the energy.
But any interior modes is not, the observer is not in the future diamond of the interior modes, right?
Can you say it again, please?
So any asymptotic observer doesn't live in the future diamond of the interior modes.
Oh, I'm sorry. This is we're still talking about the exterior here. So I'm sorry, maybe I'm not clear. So we're looking at the exterior for now. We're starting from the exterior of the black hole. We're trying to reconstruct this part of the space-time for now.
This minus omega is which modes is minus omega?
Well, I mean, you have you can define the modes. Well, you can quantize the field on slices here, right? And you have creation and annihilation operators. And the annihilation operators have a minus sign in the commutator of the Hamiltonian.
They will have plus k and minus k, but omega is supposed to be positive.
Omega is always positive in my conventions. So I have sort of, you see here, the integral is from 0 to infinity. Well, I mean, you could, in some sense, you could think that b of minus omega is b omega dagger, right? So I'm always working with positive omega. Okay, now the question is, what happens if we have a pure state? So the first thing we want to establish is that there is something like a large n factorization on a pure state. So we can discuss it if you want, or we can move on. I don't know. So the assumption here is that if we take n, small n, single trace operators, where small n is small compared to capital N, and we compute a correlation function on a typical pure state at high temp energies, this will factorize the two-point function on that state. This is not entirely obvious, but it's sort of,
How do you show something?
yeah. I cannot. Yeah, so I cannot prove it, but I will give you some the plausibility arguments, right? So the first statement is to start with that pure state, psi, O, psi, and use the theorem that I mentioned yesterday, which says that this is exponentially close to the macrocanonical correlator So yesterday we actually sort of outlined the proof of a theorem that if you have a typical pure state and you have some operators inside, it's, you can approximate them very well by the microcanonical density matrix, up to exponentially small corrections. Okay, so this step is very robust, right? Then the next step is to replace this microcanonical density matrix with a canonical density matrix, which is a little bit more subtle because now the corrections are of order 1 over n, right? 1 over s. These guys we can think of as correlators, and we can now weak rotate to Euclidean signature, and then we have some correlators on the S3 times S1, and they are single trace correlators. So we would expect there that Larsen factorization holds. But there's a subtlety that we have to go back to Lorentzian signature, and that involves analytic continuation. So in principle, it could be that certain 1 over n corrections get amplified upon analytic continuation. In fact, that happens when you look at these chaotic correlators, these out-of-time order correlators. But in that situation, the time scales are long, right? You go back to Lorentzian time, and you have to separate the operators by scrambling time in order to enhance the 1 over n corrections. So the hope is that if you restrict your attention to correlation functions at time separations which are of order 1, then larger factorization will continue to hold. But I don't have a more robust proof than what I just said. Maybe somebody knows, but I mean. Also, like in situations, like there's some, well.
Euclidean, this would be completely correct.
Well, there are
some properties of O's, right? That
yeah, they have to be single trace.
Prevent the selection of the microcanonical ensemble.
Right. Also, like in the two-dimensional CFTs, there are these computations where you can use the large central charge expansion of the Virasoro blocks, and in that case, you can check that this is actually true. But of course, that's not a proof because it assumes that the identity block dominates, which is an assumption.
Just a quick comment.
Yeah.
There was this paper yesterday by Zhibudev.
Yes.
Which was quite interesting. It was talking about how precisely you can go from canonical to micro.
Yeah, right.
And
Yeah.
No, not here. He was talking in a 2 dimensions. He was talking about Cardi formula.
Yeah.
How precisely the Cardi formula, which is precise statement of partition functions, can be made into a statement about growth of states. It's kind of ingenious.
Yeah. Okay, so everything I'm going to say from now on relies on this idea that this argument can be made precise, and then so we have that the endpoint function where small n is much smaller than capital N factorize the 2-point functions, but of course these 2-point functions are not going to be the 0 temperature 2-point functions, they're going to be the finite temperature 2-point functions. So then, if we have a correlation function on the pure state, we can approximate it up to 1 over n corrections by factorizing it into products of thermal 2-point functions. And what we will also use about these 2-point functions, well, we can't really calculate this like in a strongly interactive theory, but we know that they obey the periodicity in Euclidean time, which we also call the KMS condition. So if you shift the imaginary time by the time by minus I beta, then you get the same correlator up to the change of the ordering of the 2 operators. This is an exact statement which holds well without any approximation. Okay, so now let's
When continue to Lorentzian time would imply decay of the correlator.
This property you mean?
Yes. I'm thinking periodicity like a sine to Euclidean time looks
I'm not entirely sure. I mean, periodicity decay. So this would be true even for a harmonic oscillator, right? Where there's no decay. I mean, maybe there's decay, but the recurrence is really, really fast. So this is an exact statement which does not assume that the system is thermalizing or. It would hold even below the Hawking phase transition, for instance. Yeah. Okay, so now let's try to reconstruct the local bulk field from the boundary point of view. So we have these single trace operators, and we fully transform them again on the boundary. And this condition that I wrote down before, the KMS condition, implies that there is some relationship between the 2-point function of O dagger O and O dagger. So this is the fully transform of the previous of the periodicity in Euclidean time. You just get this relation that if you change the ordering, you get this factor. And then so Okay, so here, so remember, what we want to get is the bulk modes. We want to get B and B dagger in the bulk. And B and B dagger were normalized so that B dagger commutator was equal to 1. I mean, there was a delta function here, but that's not very important. It's proportional to 1, let's say, right? Now, these guys O and O dagger that we have defined, the Fourier modes of the single trace operators, because of Larsen factorization, what we know is that inside the correlation functions, O dagger, the commutator, is going to be a C number. It will behave like a C number. This follows from the fact that the correlators factorize.
I see.
Yeah, from up to 1 over n corrections, right? So there's some number here, which is related to the 2-point function. So you can take the expectation value here, and then you get that this C number is the 2-point function O dagger minus O dagger O. But those are related by the KMS condition. So then if we want to fix the normalization of the O in order to identify it with B, we just have to divide by the expectation value of the commutator. So at the end of the day, we get this type of definition. So we take this, we normalize these O's by dividing by the expectation value of the commutator to ensure that this is true. So now we have ensured that that guy is true, right? And then if you now calculate the expectation value of B dagger B defined in this way, you get that that is equal to the expectation value of O dagger O divided by, so there's the square root. You multiply two of these guys, the square root goes away. So it's divided by the expectation value of O dagger commutator. And now, if you use a KMS condition, the 2-point function, which is actually unknown, we don't know it. We only know that to obey the KMS condition. But the unknown 2-point function cancels in this ratio, and you're left with a Boltzmann factor that you expect. Okay, so in this way, we can understand the thermal atmosphere of the fields outside the horizon from the Fourier modes of the single trace operators on the boundary. Okay, so this is the candidate for the mode B, and then we can go back to the previous story and plug it. Yeah.
Moreover, you have shown it subject to the assumptions for a pure state.
Yes, for a pure state, that's right. So now we can go back to this formula we had and express the CFT operator in terms of these O's, where I'm sorry, the notation is not very good. Here I have absorbed the normalization. Yeah.
This KMS condition and so on, that I knew about it for a thermal ensemble.
Yes.
But it's true also for
The pure state, you mean?
pure states?
Yeah, so the reasoning is the following. There's no proof, but the reasoning is the following. We start with a pure state, and then first of all, we argue that the correlation functions will factorize to the 2-point functions. Then the 2-point function can also be approximated by a similar argument by the thermal 2-point function. Modulo the subtleties about the analytic continuation. So we don't expect that on a pure state we will have the KMS condition as an exact statement. There will definitely be corrections, but those corrections are not relevant for the type of calculations we're planning to do.
In particular, this KMS condition would say that there's a singularity around
Exactly. So singularity around the circle, which is not going to.
that can't happen.
Right, but you get a spike. You get a very high spike, which in the larger limit becomes more and more like a singularity.
Because when you're periodic, you know, two operators come together as a singularity. When two operators come together, also translated by beta, there's also a singularity because in the thermal thing, that's the same point. But here, if you do that, you take the correlation function, analytically continue it. I think you probably prove that there cannot be another.
That's right. But the statement is that you get, in the larger limit, you get something which looks more and more as a singularity. You get a very large spike at that point, and in the larger limit, this spike becomes more and more sharply peaked. So that's right. That's right. They have talked about that.
He computed the 4-point function heavy line,
Exactly.
which is that, and he said that if you suppress 1 over C corrections, it gets this periodicity, but the 1 over C corrections will smooth out.
Exactly. Right. Yeah.
And actually, it was that was motivating my first question, which was in his context that periodicity was tightly related to decay.
Actually, I'm not. At the moment, I'm not sure about the connection between the two in their paper.
Your statement was very convincing.
Yeah.
The harmonic oscillator
Right.
is exactly periodic,
Right.
so there's no decay.
Right.
So it's clear that there's no tight connection. But in that context, I think that was. I mean, I think smearing out that singularity and removing complete decay were related. His problem.
Yeah, I remember that was the motivation of their
Yeah.
work, but I don't remember the precise argument that links these two properties. I don't. Yeah.
And it's clear that it's not general
Yeah.
because of your point.
Okay, so now we can now use these objects, and then we can define this guy, phi CFT, where we use the Fourier modes again of this single trace operators of the boundary, and provided that these approximations are true, then we find that correlation functions of this guy on a pure state are going to be very close to those that you could calculate on the Hartley-Hawking state on the classical black hole background.
And also there, I think Shiran made a comment about correlator two-point function having a cut, right? Where was this cut in this beta diagonal two-point function?
It's just the fact that there is a mode, like something like an on-shell mode at every omega. Means that when you can calculate the two-point function, Kutkowski's rule,
Intermediate
yeah.
state.
Right.
Yeah.
Yeah.
It's sort of odd because large n makes it like single particle, and single particle in a finite space, you expect to have singularities only at discrete points, but the black hole does that.
Yeah. Okay, so we have this formula, and the claim is that this formula, yeah.
Black hole boundary conditions are not like finite space.
Yeah, not like finite space, right? Even though the field theory was on a scale.
Right. So the claim now that this equation sort of reproduces the semi-classical quantum field theory correlators on the black hole background, and in particular, what I think this also implies is that if the previous approximations are correct, then this also shows that the classical geometry in the exterior of the horizon cannot depend on the microstate. So in some versions of the Fuzzball proposal, there have been suggestions that the geometry may be modified even outside the horizon, like some distance outside the horizon. But if you can show that correlation functions of an object like that in the CFT have very small variance with respect to psi, which is something you could try to prove in the CFT, that would impose constraints on any possible modification of the geometry outside the horizon.
Something really simple because I thought about this so much. So since you put no boundary conditions at the horizon, then the way you have quantized it, if I actually took a physical disturbance meeting the normalizability condition at the boundary, wouldn't it result in a diverging stress tensor by the time you got to the future horizon, because it wouldn't be purely uniform?
You're going to take a superposition of Fourier modes, right? No, I think it's finite then.
But usually, if it's not purely ingoing at the future horizon, then things will blow up, right? That's the usual condition, isn't it, for the finiteness of the stress tensor, that things should be purely ingoing at the.
Yeah, I'm not sure. I think if you really take a wave packet, if you superimpose many frequencies, a continuous range of frequencies. Yeah. Okay, so near the horizon there are some oscillations, some wild. I mean, if you take a particular mode, it oscillates very rapidly near the horizon. But if you superimpose many of those, then these oscillations wash out because of some Riemann-Lebesgue type of argument. And I think if you calculate the stress tensor, it's going to be finite both on the past and the future horizon for a wave packet. So I'm sorry, maybe it was not clear. So we have quantized the field in this way, right? Yeah. And then we try to put an excitation on top of that of the thermal background, right? And you can do that by acting with something which is an integral over all frequencies, some function times b omega dagger. And
I mean, I'm just saying because something coming out of the black hole, right, is the usual argument, with a fixed omega far away is very high frequency near the black hole horizon. I was just wondering whether the stress tensor, because of that, will just be very high energy.
I was thinking that these are going to be like Feynman that at least I was totally ignorant, but I was thinking something along the same lines. I was thinking when you compute correlation functions, don't you get these Feynman type boundary conditions, which means that though you have both modes going in and out of.
So I will be talking about Whiteman correlators mostly, right?
What? Sorry?
I will be talking about Whiteman correlators mostly.
Whiteman correlators.
So these are not time ordered, right? They can be out of time ordered.
Okay.
They can have all possible orderings. But I think this question can also be addressed in regular space, right? So in regular space, we have a similar situation. We have the horizons, and we have a continuous spectrum if you expand on the regular waves. And I think there is no divergent stress tensor if you create an excitation by using a
nice Minkowski excitation.
I think you can actually, I think you can find nice radial excitations. So excitations which are localized purely on that side. Of course, they come from the past, right, and they fall into the future. But they have no support on that side. I mean, but any unitary that you act with on the left, on the right side, if you act with a unitary on the right, on the Minkowski vacuum, this state, you can find examples of states of this type which have finite Minkowski energy. And it's clear that such a state will not affect any correlation function on the left. So any excitation, yeah.
Those are nice, but what if there was something coming out?
It's coming out of the past horizon.
Past horizon, so roughly coming out from the past horizon is fine, and falling into the future horizon is good.
Yeah.
But the other way around is bad.
Yeah, I think
This is the exactly.
that's right.
And it seemed to me that the modes you considered had both. If I just look at the future horizon, had both things falling in and coming out of that. That's what was bothering me. This would be fine.
If you're asking whether the wave function has a mode which would, so there are modes which are highly oscillating, but if you put them inside integrals over frequencies, you can apply the Riemann-Lebesgue lemma, which says that if you superimpose many exponentials which oscillate very rapidly, in the limit where the rate of the oscillation goes to infinity, it washes out to zero, right?
I'm sorry, Kiran,
Yeah.
just because
Yeah.
I have the same question.
Yeah.
If I take a little wave packet that's moving very near the horizon and skimming the horizon,
You mean
just classically, forget about quantum mechanics.
you mean like this? You
A
would
little wave packet that's going along the future horizon,
okay?
going to infinity.
Yes.
So it's a little
Makes
localized
it way
around.
out. Suppose it makes its way out.
Oh, you mean a little bit outside? I'm sorry. Yes. Yes.
It's localized both in and out, let's say.
Okay. Yes.
Okay, and going. Isn't there something funny about it?
Yeah, I'll tell you what's funny about it. If let's take the wave packet to be entirely outside.
Yes.
Suppose it makes its way finally
Mm-hmm.
very far away, and it has some frequency omega.
Mm-hmm.
Now, if you compute the energy as seen when it was close to the horizon, that will be genuinely big. As in genuinely meaning, I think the energy seen by gravity for back reaction.
Yeah. So
will
that
be
should
really,
factor.
really big.
Yes. It's just that if it made its way out, it's come from some, its proper energy is.
Yeah. This is what is bothering me. Whereas, if something were falling in, and its frequency as seen very far outside initially was some finite amount, then yes, it might seem as if it has a big frequency, but actually it's just the wrong frame. You take the
Sorry, isn't that symmetric? I mean, what is the difference?
No, the asymmetry is that something.
He's saying, Sandeep saying, this is funny and this is funny. But this is okay and this is okay.
Yeah, but we're not considering these modes which are highly localized near the horizon and barely make it out, right?
What in your boundary conditions has your
What is preventing it in the boundary condition?
Well, I mean, first of all, when you expand the field in all kinds of modes, you will have your integrated overall frequencies. Okay, that's fine. Now, you want to add an excitation on top of that, right? The claim is that if you try to construct an excitation which is highly localized near this horizon using this expansion that I used, you will indeed find that it has very high energy, if that's your question.
Okay.
Local energy, I mean. But we're not going to excite these modes right now.
I'm just wondering, are you going to put those modes in the vacuum? And these
No, these modes are thermally populated, right?
those modes are probably
If I put them in the vacuum, I think that will actually cause problems because it will. I'm not sure how exactly you define those modes, but if I work in these Fourier expansions with respect to omega, these modes have to be thermally populated.
okay. I just say one other thing.
Yeah.
Which is that if you compute ordinary time-ordered correlation functions, the boundary condition essentially put these modes in the vacuum.
Yeah, okay. That may be a prescription to calculate time-ordered correlators.
Yeah,
But-
it's like you get Feynman type boundary conditions, which seem to make a lot of physical sense.
Okay, so the statement here is that if, for example, we start with, so if we want to reproduce this prescription, this expansion will correctly reproduce the time-ordered correlators,
Good.
right? So in addition, it will compute some out-of-time ordered correlators. Okay. So now, yeah.
These are precisely the modes that where they were very high energy, Hawking did put in the vacuum. Right?
Yes,
Hawking said.
yes. He put in the vacuum, and then finally they show up as particles.
Yeah.
But near the horizon, they are in the vacuum. Right?
And I thought this be basically the Hawking radiation.
So that's right.
That's why I felt these things should be in the vacuum.
Yeah, no, I think you're right. I just thought when he's saying they're in the thermal bath, he's saying it vis-a-vis the analog of
Yeah,
the
so
regular one.
I think maybe I'm a bit confused about the question, but the expansion we're doing here is exactly the same that Hawking did when he analyzed the problem using the eternal black hole. So it's not different from that.
Yeah,
So
so I think there must be some language in which.
Yeah, probably what you're saying, that's right. So probably if you, the way you're defining the modes, they're probably in the vacuum, but if you expand them in terms of this eigenstates of this omega, of this killing vector field, then they're thermally populated.
Yeah, I think his question is, how do you see that mathematically? But later.
Yeah, okay, maybe I have to think a little bit about this.
Just to say one thing, Yushigon, I now understand that you're looking at the modes as the Rindler observer would see.
That's right.
And he would see the Minkowski vacuum to be thermal. But what would reassure us is that it is really the Minkowski vacuum, which I'm a little, but presumably it's all consistent.
Yeah, so I mean, to do that, you would also probably have to work to also use the mode slightly inside the horizon to make a wave packet like this one. And then if you use both the B and the B tilde from the other side, then those will be in the ground state. Maybe that's what you mean.
Yeah, the local vacuum.
That's right. So for the local vacuum, you would use a different combination of these B's than the one that would be relevant for the Rindler observer. Okay. Okay, this will take us a little bit off topic now, and we're getting a bit late. But let me just mention it very quickly. So I mentioned earlier that these modes. So there was this.
Last, just to say it again. In this semi-classically, forgetting about Anderson company.
Yes.
Semi-classically, in one of these vacuums, in one of these states, if you had an infalling observer, you wouldn't see anything funny.
We have not yet talked about the interior. So just from what I have said so far, you cannot answer that question, I think.
No, not from the horizon. Semi-classically in gravity.
Oh yeah. Sorry, one second. Semi-classically, you mean including the quantization of the field?
Yeah.
No, you cannot answer that question with what I've written so far. Because the infalling observer would also see the bit daggers. Are you asking me slightly before the horizon? Yeah, okay. If you calculate the renormalized stress tensor on this quantum state, you will find that it's finite. And for a big black hole, it goes to 0.
Yeah, so again,
So there's no firewall.
No. And as you approach the horizon from the exterior, you don't notice any stress tensor which is very high near the horizon.
Fine.
Okay. Okay, let me skip that slide. If you're interested, I can mention it later if you have time. Okay, it's a little bit a side remark, so let me skip it for now.
Sorry to interrupt you so much, Kirill.
No, it's great.
Half of what you say.
It's very. I really enjoy it. I really enjoy it this way. So okay. Now let's now see what happens when we go behind the horizon. So here, I'm sorry, I have switched notation a little bit. So because I want to make contact with the CFT. So before we use B, right? Now, but let me just call it O because we identified B with O up to some normalization. And now, if we want to be able to continue the spacetime behind the horizon, and if we consider an infalling observer, and we want this observer to not notice anything when crossing this horizon, you need to have a new set of modes on the other side that we will call O tilde. And now you can work in effective field theory and try to calculate what are the properties that these operators have to obey in order for the correlation functions of the infalling observer to be smooth. And the same as those that you would calculate on the eternal black hole. So then you find that these guys obey the usual algebra. Here I have dropped the normalization. So these are supposed to be creation annihilation operators. The same thing should be true for the guys behind the horizon. The two have to commute because they're space-like separated. And they also have to satisfy certain commutation relations with Hamiltonian, which relate to the question which was asked earlier. So in particular, the operators outside the horizon have the usual property that you act with a creation operator, you increase the energy. While these O tilde guys, if you compute their commutator with this Hamiltonian, you find that there's a minus sign relative to that one. And as we will see later, this is the source of many problems. Yeah.
This is one small thing which I'm confused about. If you allow me to draw the thermofield double of the eternal black hole, I would have thought your Hamiltonian also has to be extended to apply, then there's a full, and then
Indeed.
It's that full Hamiltonian.
Indeed. But exactly. So if we wanted to do this for the eternal black hole, there wouldn't have been a problem with this equation. But now our goal is to understand the one-sided black hole, because we have a pure state in a single conformal field theory.
Okay.
But from the local analysis, you get that this equation has to be satisfied. The way you derive it is you identify the Hamiltonian with a killing isometry of the space-time, and then you just calculate the commutators. I mean, this isometry acts in this way, right? It's a space-like isometry in the interior, and you can calculate this commutator in effective field theory, and you find there's a minus sign. So this is a bit surprising because it means that you can add particles behind the horizon and lower the energy of the Hamiltonian, of the CFT. Maybe one way of thinking about it is that behind the horizon, this Hamiltonian acts like translation. It's a space-like generator. So,
How do you define vacuum inside the horizon in that case?
well, we assume, so we take the field phi, right, which is defined both in the exterior and the interior, and we fully transform it, right? So this defines for us these operators, O and O tilde. They're just defined as the Fourier modes of the field.
There is no problem of doing minus infinity.
Yeah, okay, you have to be a little bit careful about minus infinity, and you may have to consider a Fourier transform which is truncated at very large times, but this does not, we have checked that, right? This does not introduce big modifications to the conditions that you need. So here I claim that this is a local analysis, which means you have to assume that the horizon is smooth for well, not forever, right? But at least for a large enough kind of interval. And then you get these equations up to some small corrections, perhaps, which would come from the fact that you may want to limit the Fourier transform in a time bound of the boundary. For example, if you form a black hole by collapse, then it doesn't make sense to do the full Fourier transform because the interior exists only in the future, not in the past. But this will not modify the statements qualitatively.
And just to understand what you did was you took the bulk field,
Yes.
you mode expanded
Yes.
it into the
Actually, I did that. It can be done a little bit more carefully. You don't. You do it like the other way around. You start with a field in position space. You assume that it obeys some. The correlators of that field are smooth and locally look like flats, like the vacuum. And then you Fourier transform those conditions to Fourier space, and you get that the Fourier modes that you define by Fourier transforming have to obey these equations up to some small corrections which come from the fact that the horizon may be, may exist only in the future, for instance.
So you haven't yet defined what this OTILDE are.
No, exactly. I haven't defined it. I just have defined that I need to find an operator O tilde. I don't know what it is. I just have to find it exactly. I'm just trying to like list the properties that this O tilde has to obey. So this is the algebra.
Is it going to be HKLL type again?
No, not at all. I mean, the way that you will link this O tilde to the local field will be HKLL, but this is not going to be a single trace operator, if that's your question. It's going to be very different from that. Okay, so we have the algebra that these modes have to satisfy, and we also have some correlators that have to obey. So in particular, these guys in the exterior have to be thermally populated. The interior guys have also have to be thermally populated, and also they have to be entangled in a very specific way, which means that the two-point function of these guys has to be this one, right? So the last result comes from the condition that maybe that's what Sandeep was asking, that we need to obey this property. If we want the horizon to be smooth for an infalling observer, we need to have the condition that this combination annihilates the state. So this is the usual combination that you get by doing the Bogoliubov transformation between the Rindler-like observer and the infalling observer. And that condition is what is reflected by this equation together with those.
Now when you're saying all this, you've assumed that there's some translation between these abstract O's and O tildes and what you're going to call space-time. This is basically the condition that the vacuum there is the Minkowski.
Exactly.
But how can you say this abstractly unless you know
I'm saying,
how you're going to build space-time out of O and O tilde?
yeah. So I'm saying, So I'm saying, first of all, let us assume that there is a smooth space-time behind the black hole horizon, right? Then, and there are some quantum fields propagating on that space-time, right? I can take those quantum fields and expand them in modes. I have not yet told you what those modes are in the CFT, right? We have not made this connection yet. But whatever these are, they must obey these conditions if we want the space-time to be smooth.
Good. So at the moment, I'm just thinking of O tilde as coming from semi-classical analysis is the bulk.
Yeah.
Well,
and then you can later identify it with some field theory modes.
exactly.
So this equation has come from semi-classical.
Exactly. So we have this result from some classical analysis, and then if we assume that the CFT can describe the interior, there should be some operators O tilde in the CFT which obey these conditions.
So another is the definition. So this number operators of O and O tilde,
Yes.
both look like completely thermally distributed.
Well, I mean, are you worried about 1 over n corrections?
Oh, so you are okay.
So these are statements at large n. There will certainly be 1 over n corrections, and corrections for the reasons that you mentioned earlier. But those corrections, we will see that there is a problem already to leading order, at leading order. And we spent quite a lot of time trying to see whether the 1 over n corrections can sort of fix the problem, but I think they cannot.
What was the kernel in the definition of O?
Say again, please. What was
Kernel in the definition of O?
the kernel?
Yeah.
You mean?
There is F beta.
I'm sorry. This one?
Yeah.
Oh, these are these are solutions of the Klein-Gordon equation on the AdS black hole background, which are normalizable at the boundary and no boundary conditions near the horizon. So in the case of BTC black hole, you can write them down explicitly. There are some hypergeometric functions. In higher dimensions, you cannot calculate them. Okay, so now the philosophy is that we start from the bulk, we get some conditions that we need to satisfy, and then we try to identify these objects in the CFT.
And the bulk field inside the horizon is related to O tilde by the same transform?
That he didn't tell us. Yeah.
You mean this one of this type?
Yes.
Yes, a similar one, not exactly the same. I will tell you in like. Do you want me to tell you now? I can tell you now, but.
Now is good.
To derive this condition, we have to know, since the condition came from the bulk.
Yeah, of course,
you
of
can't
course.
derive this without knowing how.
Okay,
That's what I was also
okay,
wondering.
it's far away, so
Because
now.
that's an abstract way of saying that.
Yeah, so we assume that there is. Okay. So the final formula will be very similar to this one. So you will have an expansion of this form plus another term where you have O tilde multiplying, let's say, G, some other wave functions, which correspond to solutions of the Klein-Gordon equation in the interior. They're twice as many because you don't have the normalizable boundary condition to impose, right? So when you expand the Klein-Gordon field in the interior, you get twice as many solutions as those that you had in the exterior, which sort of makes sense, right? Because there are things coming from the right and things coming from the left. And then we will add another term here, which will be of the form G times omega tilde.
So what is O tilde in CFT?
That's the big question we want to address. That's the main point of. So everything else I'm saying is sort of assumes a bulk. It's not a derivation of the bulk, right? So the non-trivial question is, can we find operators O tilde with these properties? That's the non-trivial question.
F was well defined only in this wedge.
This one?
Yeah.
Sorry. No, I'm sorry. This is not.
Sorry, in Penrose diagram.
Yeah. It's well defined only in the exterior. It's highly oscillating.
Exterior of both.
Yes, that's right.
Okay, and okay, fine.
And sorry, so now that you brought it up, you have twice the number of modes in the interior.
Yes.
And omega, because it's the eigenvalue for a spatial translation,
Yes.
it takes both positive
Exactly.
and negative values.
That's another way of understanding this equation. That we can get a minus sign because it's more like momentum in the interior, so it can be both positive and negative.
Thank you.
Okay, so deriving these equations and then arguing that if you combine O and O tilde in an 8-Cayley-like prescription to reconstruct the interior is sort of trivial in the sense that we assumed the bulk, right? The non-trivial part of what I'm saying is whether and how we can find these operators O tilde in the CFT.
I'm just trying to understand
Yeah.
the trivial part first. That's
Yeah.
just kinematic.
Yeah.
So if I take this F,
Yes.
for one of the two signs of omega, can I easily analytically continue it here? And the other two signs of omega, the other sign of omega here. What I'm thinking is that, some kind of modes that are ingoing, you should be able to go take in there.
That's true.
And modes that are outgoing, you should be able to
That's
take
true.
in there.
That's correct.
Okay. And then the other F will come from the other side.
That's correct.
Okay, so now I understand.
Yeah. Great. Okay. Okay. So
Yeah, imagine that's a journal black hole.
yeah. So in the case of the eternal black hole, we can identify these O tildes as the O lefts. It's sort of obvious. In the case of a collapsing black hole, what would be? I think nobody has done it carefully, but so if we have a collapsing black hole, these O tildes will be the modes which are coming. These modes here, right? So in principle, you could trace them back and see where they came from in the CFT. So they would be at some point in the CFT before you threw in the matter to form the star. So yeah, yeah.
And then they would have a Transplanckian collision.
That's right.
That follows.
That's right. So because of that, we don't know how precise that calculation would be of extrapolating these guys to the past and using effective field theory to identify what they are in the CFT. So probably, if the black hole is not, I mean, if you look a little bit after the collapse, this Transplanckian factor is not going to be very large. So you may be able to do it for, slightly after the formation of the black hole. But if you try to see what happens at late times, when an infalling observer jumps very, very late, this Transplanckian factor keeps growing, and probably we will lose control at some point. But nobody has done this carefully, I think. But yeah. So the point is that when you have a particle moving along the horizon, it gets redshifted. So if you want to find a mode here, which has frequency omega, which is order 1, for example, and you try to trace it back to see where it came from, as you go back in this diagram, it will get blue shifted. And in particular, this happens exponentially fast, which means that if you start here at very late times and you trace back a mode of low frequency, it will have ultra-Planckian frequency when crossing the star. And then the effective field theory calculation will probably be unreliable. So one-over-n corrections will become important, and so on and so forth.
Sorry, because I thought about this once, but I wasn't sure where to take it. When you say no one's done it carefully enough, what
Oh, yeah, no, I'm sorry. I meant in AdS CFT. Nobody has done it in AdS CFT. Well, you could try to ignore this Transplanckian problem for now. For example, start with at the level of the free field. Just ignore interactions completely. You could try to take the mode here and just propagate it backwards and express in terms of this some operators on the CFT.
But that's probably straightforward.
Yeah, it's probably straightforward. That's right.
So this state in the CFT is going to be as heavy as a black hole?
You mean this thing, the Transplanckian? Well, this energy that we're talking about is the local energy, right? It's not like the energy measured from the point of view of the boundary. But it will be not only that of the black hole, it will be much bigger. It grows exponentially. So the energy at the center of mass of the collision is unbound. I mean, it keeps growing forever. Okay, but so there's this issue with the Transplanckian problem here that we cannot perhaps do it reliably. But apart from that, there's a bigger issue, which is the following. As we argued yesterday, or Tuesday, the black holes that you form from collapse, yeah.
You're going to impose this condition or not?
This one?
Yes.
Yes.
Wasn't that the condition that near the horizon, the state was locally in the vacuum?
The state was in the vacuum.
Well, that will be true for like before without the star, right? If you have the star, then that will not be the case. So this will be true for an equilibrium state.
I see. So you're going to excite states above this later on.
Later on, yes, that's right.
Okay. And those will have trouble.
If you try to do the calculation of this type, yes.
Yeah, these are precisely the states that don't have the Transplanckian problem.
They're empty. They're just an empty horizon. Yes,
Yeah.
exactly. So, but also you can think of this equation as the equation coming from the analysis at very late times on a state which had a star in the past.
Yeah.
So if you take this geometry and you try to, you can go arbitrarily far towards the future, right?
Yes.
And then you can do an analysis there, very, very, very far.
Yes.
Then you will get again this condition. Not exactly, but approximately.
Everything is decayed away.
That's right. That's right. But okay, now there's this issue.
Everything is decayed away precisely because at early times you didn't allow huge energies.
You mean as on-shell particles? Yes,
Yes.
that's right. That's right.
What I was saying was just if you wanted to trace the modes back, then you have this issue.
Yeah.
Reconstruct the modes or the operators.
But if you're going to, sounds like the same issue Hawking had.
It's
Yeah,
the
of
same
course.
issue,
Yes, that's right.
But here you're trying to identify the dual operators carefully.
Right. Let me emphasize that this is not what I'm going to do in the next of my slides, right? So this is something that could be done, but we haven't done it.
I understand, but
Yeah.
just to understand.
And also to answer your question, even if you send something Transplanckian or very high, eventually it would also equilibrate. So you just have to wait longer.
I understand.
Right.
I understand. Yeah, but you could fixing any time, you could always make an energy large enough at initial
Yes,
time
that's
so
right.
that it hasn't decayed.
That's right.
And the condition that you've decayed away is that you didn't have those arbitrary.
That's right. That's right.
Yeah, but I mean, we may not have to be very careful about defining these modes if they were always in the vacuum where your Transplanckian physics, where your collision happened.
Yes, okay, but then, so the following issue is, there's a following issue that, first of all, the type of black hole that you will get in this way, as we discussed yesterday, on Tuesday, is not the most general black hole you can form at a given energy.
Yeah.
Right. So, yeah, so it is this point, that the black holes formed by simple, when I say simple, I mean you prepare a star and you let it collapse, gravitation collapse, are atypical. So they're a small subset of the total number of states which are counted by the biggest Hawking entropy. And that we sort of discussed on Tuesday, that you estimate the entropy of a gas of gravitons in AdS, and you compare it to the entropy of a black hole, or you can even do it I mean, this was done, I think the first estimate was probably by Tofts in the early days, where he estimated, he took a cloud of, like a star at finite temperature. You calculate the entropy and the energy as a function of the temperature, and then you find the relationship between the entropy and the mass, and you get, yeah. So for a star, it's like m to the 3/2. For the black hole, it's m squared. So there's a factor there. Oh, it was Bekenstein?
Yeah.
Okay, sorry. I'm sorry.
No, it's okay. Yeah.
How does one make the black hole?
How does one make the estimate?
The other black hole?
Oh, the other black hole. Yeah. So the other black hole, okay, I mean, first of all, from the point of view of the CFT, we can just start with any state we like, right? We don't have to necessarily explain how we prepare it. But you could also, you can also do it in the following way. You form a black hole by collapsing a star, and then you start perturbing the black hole by throwing in particles, which you can produce by single trace operators, and also remove particles. And you keep doing it for a very, very long time. And if you do a complicated enough procedure, you can probably approximate every microstate you want. Or in principle, you can act with a very complicated primary of very high dimension, and you just get the state, right? I mean, formally, you can just write down the state. So even if you could solve a problem by an analysis of this type, that would not address the question of what happens on a typical state. So let me also say again, I think we discussed it on Tuesday. It could be that the problems we will find later imply that a typical state has no interior, but a collapsing black hole at early times has an interior. So that's a logical possibility. But we will try to prove in the rest of my talk that even typical black hole microstates will have a smooth interior. Okay. Now, typical black hole microstates, we already defined it yesterday, Tuesday. They're defined by taking a random superposition of energy eigenstates, which are selected in a window of energy, which is sharp. And these guys are selected randomly with a measure that I defined yesterday on Tuesday. And now it's not difficult to estimate that to show that if you take any operator A and you calculate the time derivative of A on the state psi, you get something which is exponentially small. The way of proving that is that these phases of these guys are uncorrelated to the phase of the observable A. So you have a sum over many, many, many complex numbers with random phases, and if you estimate the size, it turns out to be exponentially small. So this is true even if the observable A is a complicated one, as long as A is not correlated to the state. So this means that if you select randomly a pure state from the CFT, it will look like an equilibrium state to very good approximation.
The deviations of the expectation value of A from the thermal ensemble are about e to the power minus s or e to the power minus s by 2?
Sorry, from the thermal or the microcanonical ensemble?
The most stringent one, whichever, the one that will give the smaller error.
That's the microcanonical. So you're asking if it's e to the minus s or e to the minus s over 2?
Yes.
It's probably e to the s over 2.
S over 2.
Yeah.
So then isn't that another way of proving it?
Yeah. So you can, yeah, exactly. So you can prove it by referring to the previous arguments, because the microcanonical density matrix is exactly time translational invariant. It commutes to Hamiltonian, so you get this result. So in particular here, we don't have to assume the ETAs or anything more fancy. It's a more basic statement. It's the statement that the microcanonical ensemble is time translational invariant. And typical states are very close to the microcanonical ensemble, so they're also time translational invariant. So this means in particular that this type of state is not here, right? Here we have gravitational collapse. So there's time dependence here. Explicit time, there's something is happening. We can see the star collapsing. So this type of state is not the same thing as the typical state. So collapsing states are atypical. Okay. Now, yeah.
Feel free to take a break.
For me, it's fine, but I know that for the audience, sometimes it's more boring and tiring. So.
But maybe we can all have a toilet break at 11:30.
That would be good.
Okay. Okay. Now let me try. So we said before that if we have specific microstates, we can find these O tildes, which are desired properties. But now we will try to see that for these states, if you demand these equations for a typical state, then you run into contradictions.
Which equation?
I mean, we have a set of equations that we want to demand, these equations. So we'll argue that these equations are cannot be implemented. So this is a set of operator equations and some statements about correlation functions. We will show that it is not possible to satisfy these equations on most microstates. If you demand that they are true for most microstates, you run into a contradiction.
And is this Marov-Polchinski?
There is, well, it was built up slowly. One was, I think maybe it started in AMS's, so this is AMS together with Stanford, then Marov-Polchinski, and there's one more by Busso.
Like sometimes cited as Marov-Polchinski, so I just want to make sure. But okay, yeah, okay.
Yeah, I think, well, the most precise version is actually due to me and Suvrat. So we were trying to kill this argument, and trying to kill that, we try to make it more precise. So this is the most precise kind of version.
So these atypical black holes which are formed by collapse are the ones where this is possible to solve?
Maybe, and maybe for early times only. Yeah.
Just to understand it, so what you showed was, if I understand, was that at least the omega operators for a typical pure state could be constructed.
Yeah. Those are the Fourier modes of the single trace operator on the boundary.
And those can be constructed.
Yeah, that's right.
Then in addition, you assume that there are O tilde
Uh-huh.
operators. And you said if we want something like a bulk geometry with a smooth horizon, those operators should exist.
Right.
Right? And now you're saying, okay, if you want those operators to exist, then the state cannot be typical.
Exactly.
Right? So
That's right. That's right.
Okay.
Right. So now I will assume that those operators exist and the state is typical, and I will derive a contradiction.
And the first set of operators were just microscopic operators in field theory. Second set of operators we don't yet know.
Exactly.
But you're assuming that they exist as microscopic operators.
What do you mean by microscopic operators?
Meaning that they exist as operators without reference to which state.
Exactly. That's right.
So this would be saying that a typical black hole has firewall?
The contradiction I will derive now would, well, one interpretation would be that it has a firewall. Another interpretation would be that there is no firewall, but the CFT cannot describe the interior. This has also been formulated. Maybe AdS-CFT is not a complete, well, the bulk theory has more than the boundary theory, but that's another proposal. And the third one is that the one I will present later. So let me start with a less, the more, okay, so the more intuitive way of thinking about it is to look at this equation, and notice that you act with a creation operator, and you're lowering the energy of the CFT. But the CFT, so if we take all, if this commutator can, if we can take the expectation value on a typical state here, that means that I can take the states at energy E, and by acting with this O tilde dagger, I map them to E minus omega, right? But in the CFT, we know that the entropy at energy E is larger than the entropy at E minus omega, because the entropy is monotonically increasing with energy in that regime. So you have a linear operator acting on a Hilbert space of given size and maps those states into a Hilbert space of smaller size. That's not possible unless the operator has a non-trivial kernel. But we assumed from the first equation here that this is a creation operator. It cannot possibly have a non-trivial kernel. Or to say differently, more directly, suppose that O tilde dagger psi, we look at this state, right? And we compute the norm of that state. So we need to consider this object. Now using this commutator, we can write it as 1 plus psi, and the other ordering here. Now, whatever this guy is, I mean, this it cannot be negative. You have a +1, so this has to be positive. It cannot be 0. So this implies that O tilde dagger cannot annihilate the state. And this is in contradiction with the statement that it maps a larger Hilbert space into a smaller Hilbert space. So this is the more intuitive way of thinking about it, but we were a bit worried about possible, like one-over-n corrections conspiring maybe in some way.
This was in one of the Polchinski.
Yeah, this was in the Amsterd's paper. The Amsterd's. It's Alberi, Markovsky, the second paper they wrote. But now we try to isolate the possible error terms and loopholes, and you can derive a slightly more more precise inequality, which is the following. You define the number operator.
Sorry,
Yeah.
very stupid question.
Yeah.
Why can't that be negative, please?
This one, because this sum operator times its dagger.
Which is?
It's some operator. We don't know what it is, but we have an operator times its dagger.
This commutator plus a. I see.
Yeah.
Okay.
So that's positive. That cannot. It's non-negative.
A acting on psi or omega.
That's right. Yeah. It's the norm of this state, so it cannot be negative.
So you usually know what the commutator is.
Yeah. So I have used both this equation together with that equation, and I find that they're not mutually consistent. So I use the first equation to do this manipulation. I looked at the norm of this state, and I rewrote it in this way. Now I know that this object is greater than or equal to 0,
Yeah.
and there's a +1 here.
The guy that could have been negative, you know, is 1, basically. Right?
Like
Yeah.
if you reverse the argument for A,
Yeah.
then the
Yeah.
Right.
So the left-hand side has to be greater than 1, let's say.
So it cannot be 0 in particular. It cannot be. It cannot. So O tilde dagger cannot annihilate the state. Now the other problem was.
But it was not annihilating, it was just taking you to a lower energy state.
Yeah, but the problem is the following: that if you start with energy states of energy E, and you go down to energy E minus omega, there are fewer states here.
Yes.
So it can't possibly be that all of those states are mapped by a linear operator into all of those states. There are fewer states. So some of them have to be annihilated, which contradicts that statement. What is the argument? Oh, there's a the resolution that will later. Yes. So this is one way of phrasing the argument. Another way is to consider the number operator for these guys. So we consider the number operator, and then we try to calculate the expectation value of the number operator for the modes behind the horizon on a typical pure state. Now, there is a critical point. The critical point is that when I calculate the expectation value of the number operator on the typical pure state, I will replace this by, if this if most states have a smooth interior, then it means that this object has to be given by this one for most states. So I can, in particular, I can replace it with the thermal expectation value up to 1/n corrections. Now, I use this commutator to rewrite it as maybe, okay, let me do it. So to rewrite it as O tilde dagger e to the minus beta x tilde. Now, then I use a cyclist of the trace. I commuted these two guys. You pick up this factor because,
That has some energy.
yeah. Then I use a cyclist of the trace. And then I use a commutator, the first equation, to rewrite it as the other ordering +1. So all in all, let me call this expectation value, let me call it n, small n. All in all, I find that small n is equal to e to the beta omega times, when I change the ordering, I get back n plus 1. But now if you solve, you find that n is equal to minus e to the beta omega divided by e to the beta omega minus 1, which is negative. Which cannot be. Exactly. Which is a positive operator, it cannot be.
If you did the same with O, you get positive,
Yeah.
and
Exactly. That's right. So this is the version of the paradox that we sort of formulated with Suvrat, which we think sort of avoids some possible loopholes in the previous argument. And this shows that you cannot, I mean, this suggests that you cannot possibly find these operators in the CFT. Now you can ask why this contradiction was derived by starting with what I said before is effective field theory predictions.
Sorry,
yeah.
I thought you, sorry to say this, but you were going to say that this is derived assuming that you have a typical state, right? Or rather, isn't that true?
Yeah.
That the states where that O tilde omega could be defined for typical.
Exactly, precisely. But somebody could ask, why wasn't, if these are predictions of effective field theory, why wasn't this problem noticed long time ago? I mean, for example, even if you do an analysis at the level of Birrell and Davis, you would have these equations. Why didn't Birrell and Davis identify this problem?
Well, but they assumed you have a smooth interior, and they didn't quite ask the question you're asking, right?
Well, they would have written this algebra. This algebra would be there.
Because it's just bulk algebra.
Yeah, it's just bulk algebra. And
Why didn't they ask for the typical states?
exactly, that's precisely the point. So what they would have done is they would have demanded this algebra to be true on a particular state, let's say the Unruh vacuum or maybe the Hartle-Hawking vacuum.
Right.
Here, we have a boundary CFT which is telling us there are many microstates on which this algebra has to be realized. And this is the critical step, that I replaced this expectation value in a pure state by the thermal trace. And then I use the cyclist of the trace to derive this contradiction.
Why would they have demanded this on only one state?
Because, I mean, if you do effective field theory in the bulk, you don't see the black hole entropy as, I mean, you don't see different microstates. You just see the effective, the state of the quantum field.
I mean, somehow having the crutch of AdS, CFT, and Hilbert space is crucial.
Yes, yes. And
The fact that black hole is actually,
exactly.
Black hole is a microstate or
Yeah, the fact that there are many black hole microstates allowed us to replace this expectation value by a trace. And then we exploited the cyclist of the trace to derive this contradiction. So what I'm saying is that
you were emphasizing linearity also at some point.
yeah. So this is true, assuming that O tilde is a linear operator, right? So this is to emphasize that this paradox arises if you demand smoothness for many states. If you demand smoothness for one state or like for a small number of states, there's no there's no paradox.
Is it right that if you just take the black hole and try to put excite a thermal gas, think of it as all gravitons excited in a thermal gas at the temperature of the black hole, that would give rise to this contradiction.
Possibly, but in that case, you would not have a smooth interior, right?
No, I wanted to ask something perhaps similar. Are you saying, I thought earlier both of you had emphasized that the entropy, the number of states in the thermal gas is vastly smaller than the Bekenstein-Hawking entropy. So suppose we were to say that only the states which start off as a thermal gas which undergoes collapse form black holes, but with smooth horizons, but not typical states.
Yes.
Then we wouldn't be in any contradiction.
Yeah, then one would have to, so then you would have,
That's not what you were saying, right? But, okay.
oh, so maybe Siraj wants to repeat.
What I wanted to say was probably simple-minded, but I'm saying that suppose you think of the black hole as representing a thermal ensemble, just in gravity. Then of course we knew that in addition to the black hole there's a gas inside.
Okay.
Okay? But now if you accompany that with a gas inside, that gas inside,
Yeah, that gas will be, because of this equation, that will be unstable thermodynamically, in the sense that why would it not keep producing pairs of particles and antiparticles?
you keep getting lower and lower
That's right.
and lower energies.
Yes, that's
basically the
exactly.
heart of the issue.
Exactly, yes. You can, you can think of, like, because of this negative sign, you can create pairs of particles without any cost in energy, while you would get some entropic factor, and this would keep happening. And so this is an unstable kind of situation, it seems.
Right. But I mean, so I guess I see you're emphasizing we can't think of the black hole as gas inside and gas outside.
Okay.
Right.
So the gas inside is problematic.
Right, exactly. Okay.
Can we take a break?
Yeah, can I say one more paradox, and then we take a break. So another paradox was, yeah.
Here you emphasize the fact that because of this approximation of this thermal
Yes.
this thing that you were able to
Yes.
define from it. But previously you had an argument about the positivity or the norm
Yes.
and so on also.
Yes.
Right? That didn't assume anything, did it? That just assumed.
Oh, the previous argument assumed that you map a bigger Hilbert space into a smaller Hilbert space. So that meant that this algebra has to be realized on most of those states of these two Hilbert spaces.
You are allowing for some kernel. Sorry, you are what?
I mean, both arguments.
Yeah, you are allowing.
Both arguments, in order to derive a contradiction, require that you apply the algebra on many states, on most states. Yeah. So let me just mention one more paradox, version of the paradox, which was formulated by Busso. So it's the following. Suppose we take the number operator for the modes of the infalling observer. So the infalling observer is falling in, right? And he defines some modes, A, which count particles according to the infalling observer. So those will be Bogoliubov combination of the B and the B tilde, of the O and the O tildes. Suppose that the typical state has a smooth horizon. Then we expect that the trace in the macrocanonical density matrix at energy E of this number operator would have to be 0 or very close to 0.
Why is that?
If you assume that most states of a given energy have a smooth horizon, then if the infalling observer is falling into those black holes, he will measure that the number operator is 0 or very close to 0.
He doesn't see
At least at high enough energies.
Yes. So there may be some small deviations, but
No, because he doesn't see any particle.
he doesn't see any particle.
Okay.
So then he can take the trace, again, the trace over the macrocanonical. This is the Hilbert space of given energy.
Of given boundary energy?
Boundary energy, boundary energy.
Yeah.
So this is the Hilbert space of boundary energy E.
Sorry.
Yeah.
So basically, the infalling observer will not any Hawking quanta,
He doesn't really see the Hawking quanta because he's in free.
but the Hawking quantas are separated at horizon.
Yeah, but it's a little bit like in Minkowski space. If you are an accelerated observer, if you're a Rindler observer, you will see thermal radiation, but you're a freely falling observer.
Those Hawking quantas are actual particles.
Not according to the infalling observer, and if you look at, I mean, there is always a small kind of excitation that this guy will see. So the expectation value of the trace is not 0, but for a large enough black hole, it's really
They
tiny.
become unambiguously actual particles at infinity.
Right.
Yeah.
Not at the horizon.
Right.
The horizon, locally you have the Minkowski vacuum.
Yeah. So then if the horizon is smooth for most states, we can take the trace in the microcanonical ensemble of this number operator, and this has to be 0. Now, let us consider the number operator for the modes outside. I'm sorry, this is a mistake. There shouldn't be a tilde here. I'm sorry. This is the number operator for the modes outside the horizon. These are the modes of the thermal atmosphere outside the horizon. The point is that this guy almost commutes with the CFT Hamiltonian. Why? Well, this operator has 0 frequency, right? It's of the form O dagger. So the number operator of the exterior modes, according to the static observer, is of the form O dagger O, right? So these guys have 0 frequency if you multiply them together. So this object almost commutes with the CFT Hamiltonian. Not quite. There are 1/n corrections, but it almost in the larger limit it commutes. Right? So this means that you can simultaneously diagonalize this number operator of the exterior modes and the Hamiltonian. So you can diagonalize this operator inside the subspace. And you can select the basis of the subspace spanned by eigenvectors of this number operator. Then you can evaluate this trace on that basis. So then you can write it as a sum over all eigenstates of the number operator of the exterior modes. But on each one of those states, from effective field theory predicts that the infalling observer will detect excitations. Only if you have the exterior modes, they have to be thermally populated in order for the infaller not to see anything. If instead of a thermally populated ensemble, you take an eigenstate of a particular mode, then the infaller will see an non-shell particle.
So I'm getting confused
Yeah.
about which are the outside modes and which are
I'm sorry, A are inside. So A are for infaller,
A is not inside but
infaller, right? Infaller, and B are static observer. So static and exterior.
So I guess the important point here is that the trace can be evaluated.
Yes, in this basis. That's right. So you should think of these as eigenstates of the Rindler modes, right? These are like the Minkowski modes in flat space, and these are the Rindler modes. And we're saying if you take a Rindler eigenstate, you will see some excitation when you fall through the horizon.
Yes.
And this is going to be true for every Riedler eigenstate. So you have to sum over all those states, and you
They're
get
all
some
positive.
all positive. You get a very large number, and it totally violates what you expect.
Why does the H commute to the NP again?
Because it's a double trace operator of this form.
That's zero energy.
So if you it has zero energy effectively. This has minus.
Minus omega plus omega.
Yeah. Yeah. So again, you can think maybe there are some one over n corrections here that we have ignored. Maybe those are important. And we tried very hard with Suvra to find loopholes, but we couldn't. So
Why is this the same thing as before?
it's not exactly the same thing. It's a slightly different paradox. Yeah. So,
Again, it's probably more that the inferring observer himself depends on what the state is.
yeah. So here, to phrase this paradox, it was crucial that we work with a trace and with a fixed linear operator.
Correct. Not
And
one that-
later we will relax this assumption.
Interesting. Very nice.
Yeah.
I see.
Okay. This.
Sorry.
Yeah.
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 I
Mhm.
probably missed the main point here, but I don't know why couldn't you do the same thing for the outside particles? Why was it till that point?
No, this.
You mean you would not have the first equation, right?
So
well,
that
um,
tilde is typo, right?
This is a mistake. I'm sorry. This is a typo. This should have been O, or dagger O. I'm sorry.
The fact that the infalling guy sees nothing is only for the infalling guy.
Okay. Now since we have to take a break, I will not talk about this paradox.
Don't cut out anything, just give us.
Well, I will have to cut out this for sure, but yeah. But I wanted to stop. I wanted to stop where I present all paradoxes and then propose some resolutions. But
Don't cut it out. I mean, not for me to say, but I mean, we can go till 1:45 or something.
okay, so the final paradox, and here I stop with the paradoxes, is the one I mentioned yesterday with the eternal black hole, right? Okay, maybe okay. It's not necessary. Maybe.
Oh yeah. Okay. Otherwise, 5 minutes and we can
Yeah.
resume.
Yeah. Let's take a break. Sorry.